Here's the solution to quiz number 4 for ECE 320, Digital Electronics for Spring 2022. Now the first problem is a min-max circuit. The trick is to figure out which diodes are on, which ones are off, what the voltages are, and then what the currents are. So starting out, on the left-hand side, one of these diodes is on. If I assume the 7-volt diode is turned on, I lose 0.7 volts across the diode, and I get 6.3 volts. That doesn't work. Okay, that doesn't work because I now have 9 volts going to 6.3, 2.7 volts across this diode. I can't have two diodes on at the same time. If you do, you have a conflict and the circuit's confused. This circuit's too dumb to be confused. So taking the other extreme, if the 9-volt diode is turned on, I get 9 minus 0.7, 8.3 volts. And that works. I'm trying to push current backwards through the second diode, that turns it off. Trying to push current backwards through the third diode, it turns it off. So 8.3 volts works. Over on the right-hand side, same logic. If the 4-volt diode is turned on, I'm at 3.3 volts. And that doesn't work because I have more than 0.7 volts across this diode, it turns on. And I can't have two diodes turned on. So, if I assume this diode is turned on, I get 6 minus 0.7, 5.3 volts. And that's trying to push current backwards through this diode, it turns off. Trying to push current backwards through this diode, it turns off. Only one diode is turned on. So that's V1 and V3. Now in the middle, one of these two is turned on. If I4 is turned on, I'll have 0.7 volt drop across here, and this is 9 volts. Well, 9 volts is too much. I have more than 0.7 volts across diode 5. So that doesn't work. If diode 4 is not on, then diode 5 must be on. In which case I have 5.3 plus 0.7, 6 volts at diode at V2. And I'm trying to push current backwards through diode 4, it turns off. So that's the voltages. To get the currents, I have 8.3 volts across 1414 ohms, 5.8 milliamps. 12 minus 6, 6 volts across 10K, 0.6 milliamps. And 5.3 volts across 1414 ohms, 3.7 milliamps. Now the currents have to go somewhere. This 0.1 milliamps has nowhere to go except to the right, so I5 is 0.6 milliamps. This is 3.7 milliamps, so the total current from these two must be 3.7 milliamps. I'm missing 3 milliamps, so that's this current. And over here, 5.87 milliamps, there's only one diode that's turned on. It's got to be this guy. So that's the currents and the voltages. Problem number 2 is another max min circuit. This one's actually, the logic function for this one is this is the maximum. That's an OR function. So we'll call this ABC, DEF. This is the maximum. Maximum is OR. So this is A or B or C. This took a min function. The minimum is AND. AND D or E or F. So that's the logic this implements. Problem 2. Another max min circuit. Given these voltages, now find the currents. And the difference in the two circuits is here the diodes were facing right. If I flip the diodes, I get another circuit. So in this case, again, one of these diodes is turned on. In this case, it'll be the smallest voltage because that turns off the first diode, that turns off the second diode. I'm trying to push current backwards, so these turn off. On the right-hand side, again, the minimum works. So that turns off this one, and if you forget whether it's min or max, just guess. If this diode is on, I've got 6.7. 6.7 is too much, so it's got to be one or the other, the max or the min. This one's the min. That says the voltage right here at 4.7 volts. That between the ones in the middle, this is a max function. The 7.7 volts turns on, I lose 0.7 volts, making the 7 volts, and 4.7, I'm trying to push current backwards, that turns it off this diode. So that's the voltages. Now find the currents. 7 volts at 10K is 0.7 milliamps. 12 minus 7.7 over 1414, 3.04 milliamps. 12 minus 4.7 over 1414, 5.1 milliamps. Currents have to go somewhere. So if this current has no place to go, it has to go through that bottom diode. This current has to come from somewhere. It comes from I4. And this current then splits. Some of it goes down this way. Some of it goes right. 0.7 goes right. The remainder goes left. This is 2.341 milliamps. So that'd be the voltages and currents. Problem 3 is a clipper circuit. Given this circuit, or this mapping from X to Y, come up with a circuit that implements it. And that's this puppy right here. Let's make it a bit smaller so you can see it. So the way to design it is, first off, the slope is 3.33. That's this part of the circuit. Pick R0 for gain of 3.33. And for non-inverting amplifier, the gain is 1 plus the ratio. So I want the ratio to be 2.33 to 1. This is 2.33K. The Zener voltage. Zener 1 turns on at 5 volts, so this is a 5 volt Zener. Zener 2 turns on at 8 volts. That's an 8 volt Zener. To find R1, again for me this is 1414 ohms. Excuse me. I have a voltage divider. So by voltage division, it's R1 over R1 plus R3 times the gain of 3.33 is my slope, 0.857. Solving for R1, I get 490 ohms, so this is 490. When Zener 2 turns on, think Thevenin equivalent. I've got a Thevenin voltage, Thevenin resistance. The resistance determines the slope. And in the resistance, these two are in parallel. The slope is 0.285. Change in Y per change in X, 0.285. So 0.285 is the parallel combination of R1 and R2. Is a voltage divider with R3 times the gain of my amplifier. Solving, R1 in parallel with R2 is 132 ohms. I know that R1 is 490, therefore R2 is 181 ohms. So this circuit implements that function. Problem 4. Design a circuit that clips at plus 8 and minus 7 volts. This is kind of a gimme. Just use an 8 volt Zener and a 7 volt Zener. This will actually clip at 8 plus 0.7, 8.7 volts. To take care of that 0.7, back this off by 0.7, and back this off by 0.7. And now clip at 8 volts and minus 7 volts. One of many circuits. This is probably the simplest of them. Problem 5. So for this one, draw the load line, and then find the operating point when Vn is 2 volts and 6 volts. To start, R is 1414 ohms, based upon your birth date. That'd be Mother's Day. 20 volts over 1414 ohms gives you 14.4 milliamps. That's the y-intercept. The x-intercept is 20 volts. Connect the two with a straight line. That's my load line. When the input is 2 volts, this is 0.7. Get that's a diode. 2 minus 0.7 is 1.3 volts. 1.3 volts at 1K is 1.3 milliamps. So go 1.3 milliamps where it intersects the load line. There's my solution. So that's 10.8 volts, 6.5 milliamps, the operating point at 2 volts. When I'm at 6 volts, I have 5.3 volts across 1K, 5.3 milliamps. That intersects the load line way over here. I can't go negative. That's physically impossible. If I go negative, I'm producing energy, and a piece of silicon can't do that. So move along the load line, I can never go negative. That violates conservation of energy. And I can't even quite get to 0. Instead, I clip saturated about 0.2 volts. So in that case, since my commanded current, beta IB, is so much larger than I can get, I saturate at 0.2 volts, and the current then is 14 milliamps. Then the last one, if you had this circuit in lab, you built it, this is 1414 ohms, I measure these voltages, find the currents, find the gain of the transistor. Well, IB is just 5 minus 0.68 over R, 3.05 milliamps. IC is 20 minus 6.23 over 15, 918 milliamps. The ratio is the gain. This transistor apparently has a gain of 300.5, and I'm in the active region. I know that because VCE, right here, is bigger than 0.2 volts, so I know it's active. That is quiz number 4 for ECE 320 Electronics for spring 2022.